Hello from ChemHelp ASAP. This video provides practice problems on the addition of strong nucleophiles to carbonyls, specifically aldehydes and ketones. Check the video description to find links to printable copies of these problems and their solutions. Furthermore, links during the video will connect you to other videos that provide more detail on these types of reactions. The reaction of strong nucleophiles with a carbonyl is one of the first carbonyl reactions that many students encounter. The reaction starts with a carbonyl. In this video, we will only cover aldehydes and ketones. The nucleophile, which is often a hydride or organometallic, attacks the carbon at the CO pi bond. This reaction forms a tetrahedral intermediate. Because the strong nucleophile is generally also very basic, the solvent for this first step is often not acidic, not even weakly acidic. Therefore, the tetrahedral intermediate stays in solution until a proton source, normally water, is added in a later step to neutralize the oxyanion and afford the alcohol product. That's really pretty much it. The beauty of this reaction is that aldehydes and ketones are very common. Strong nucleophiles, including organometallics like Grignard reagents and organolithiums, are easy to prepare. Therefore, the number of different alcohols that can be made through this general reaction is huge. Additionally, the reaction forms a new carbon-carbon bond and is prized as a simple method for building up larger organic molecules. Finally, the alcohol in the product is a nice handle for additional reactions and transformations. Let's work through some reactions that exemplify this process. Okay, problem number one. What do we have here? Well, we have a carbonyl, and it's going to be attacked by this reagent, and that's an organometallic. Note that we have two steps. The first step is addition of our nucleophile, our Grignard reagents, and the second step is addition of water. That's going to be pretty typical to what we'll see in these reactions. Note there's no solvent listed for this first step. If there were, it would be something like THF or maybe ether. Those are both very common for these types of reactions. Okay, so let's get started. So this is phenylmagnesium bromide. I won't always do this for every question, but let's write out the full structure. This is a carbanion, or I like to envision it as a carbanion. And so this nucleophilic carbon is going to attack that CO pi bond. We'll go down to the bottom of the slide. There's the O- for our tetrahedral intermediate. And MgCl is a complex ion. That is the counter ion to the O-. And there's our benzene ring. You know, feel free to write phenyl if you want to. That is our tetrahedral intermediate. And of course, this reacts in the second step with water once it's added, and we form our product. So let's draw our product, and again, we'll draw it the full. You could draw phenyl here. You could write phenyl, pH, instead of writing out that full benzene ring, and there is our alcohol. Now, one thing I'll note, it doesn't matter how you draw this alcohol. First of all, this carbon right here is not a stereocenter. So if you wanted to write it like this, with the benzene ring, and I'll just write the pH, with the phenyl coming in from the side, it's all the same connectivity, exact same structure. But that's our addition product, and we get an alcohol as the product. All right, here is problem 2. Problem 2 is a little different. Note that we're given our carbonyl starting material and our alcohol product, but we're missing something in the middle. And what's going to be in this box is going to be our nucleophile. So it's kind of the first step we need to do is think, well, here's our carbonyl, and we added something to our carbonyl. What did we add? This problem's just a bit tricky because I haven't drawn in the hydrogens. But once you consider the hydrogens on that carbon, you realize, oh, there's another hydrogen that has been added to our carbonyl. So we started with 1 and now we have 2. So our nucleophile must have been an H-. And so therefore, we have a couple options in this box. I'm going to go with, let's go with one of our hydride sources. It's NaBH. BH4, sodium borohydride. Sodium borohydride is really the one exception we're going to see in this video where we tend to use this in an alcohol solvent. Sodium borohydride isn't quite as reactive as some of these other nucleophiles. It's still a source of hydride, that's H-, and I tend to tell my students just to think of this as an H- source. I'm not sure how your instructor likes you to think of this, but I just say just draw H-. That's just supposed to be 2 electrons, not 6 or whatever I drew there. Okay, so that attacks the carbonyl. And of course, as always, once we attack, we'll draw in the hydrogen. We're not required to for line angle structures, but we'll draw that in. Sodium is the counter ion, and here's our tetrahedral intermediate. You will get very tired of hearing me say that by the end of the video. And here is our ethanol. Normally we have to wait for this. This is a second step, but in this case we have ethanol present. That's a protic solvent, and it's capable of protonating our alkoxide to give our alcohol as a product. So in this problem, we were given the starting material and product, and we had to figure out what was the nucleophile that was added, and that came from sodium borohydride. All right, here is problem number 3. Problem number 3, we start with the carbonyl, and we're given the reagents, and so our nucleophile is lithium aluminum hydride. Much like sodium borohydride, I just say, save yourself some trouble and just draw in the H-. Again, do what your instructor says, not just what I say. Lithium aluminum hydride is quite a bit more reactive than sodium borohydride. Therefore, you notice we need a second step for the protonation, in this case adding water, and that means there's some other solvent for this, typically ether, or again THF would be fine as a solvent. You don't have to, I typically don't specify the solvent for this, but if you did, it's almost certainly going to be THF or ether. So we have our nucleophile hydride. We know exactly what it does. It attacks our carbonyl. This is a little bit tricky because you have this ring. Now, nothing happened to this ring. So you can just redraw the ring. And we know that H, the hydride, attacked at the same carbon where the carbonyl was. So that's going to be O-. Lithium is our counter ion. Now this is tetrahedral intermediate. We have 8 problems. There's a good chance I'll say tetrahedral intermediate in every single one of them. And this tetrahedral intermediate, it's just going to hang out because there's nothing it can do. Nothing it can do, that is, until we add water. That is a second step. That's why it's numbered separately to indicate that water is going to be held out until this reaction is complete. And that gives us our product, OH. H, and there is our alcohol. So we've added a nucleophile, hydride, to the carbon of the carbonyl. Okay, problem 4. Here we have a carbonyl. Now we have a ketone, and over the arrow, this is going to be our nucleophile, and as well as our second step for adding water. Note that if it's possible to have the nucleophile over here and the carbonyl over the arrow. There's no rule that says the carbonyl has to be to the left, although typically the more complex structure, the more interesting organic piece is going to be on the left and will be the featured starting material. Anything else will be shoved over the arrow, kind of in the co-star role. Okay, so what is our nucleophile? Our nucleophile is this organolithium reagent. I'm going to draw it a little bit differently. I'm going to draw it as a carbanion, as an ionic structure. That helps us get it into a form where we can see, it's a nucleophile. Here's this nucleophilic carbon with its lone pair of electrons. And now I'm going to attack the carbonyl. Let's see, let's draw it this way. Again, if we wanted to, we could abbreviate. In fact, when I draw the product, I'll abbreviate it a couple ways. Okay, now, so we're going to get an O- and a lithium. And let's just make note, this carbon, the nucleophilic carbon, that's 1, 2, it's very easy to drop these carbons. So just make sure you get both those carbons in your product. Now, as we've seen in other questions, oops, I got to say it. tetrahedral intermediate. As we saw in the other questions, this is going to float around until we add a proton source, and it's often water. Now, what would be a shorthand way to write this? Well, you could just say that CH3 is methyl, the 2 carbons are ethyl, and there's phenyl. So, and that would be completely appropriate, same as drawing out the product in its fuller form as we saw down here. Now, this question, this carbon, note that there are 4 different substituents to that carbon. So therefore, this is a new stereocenter. And depending on your instructor may be a little bit more strict. I don't tend to care about this as much, but some people may say, this forms a racemic mixture, because there would be 2 enantiomers, depending on whether the nucleophile, the ethyl, attacked from the top or the bottom face. That would give you 2 different stereochemical configurations there. So just be mindful when you create stereocenters. You've always got to kind of keep your eyes open for that, and especially prone to happen in addition reactions, where we're going from these flat trigonal planar carbons to tetrahedral carbons. Okay, here's a question. We have a ketone starting material. We finish with an alcohol. And what's new? Well, that phenyl group is new. So we know somewhere in this box we're going to have to show this phenyl group as a nucleophile. There are multiple ways we could do this. I'm just going to pick a way. Let's do an aerolithium. Let's do phenolithium. And of course we would need a second step as water to protonate the tetrahedral intermediate. Now, let's say you don't like organolithiums. That's fine. You could do phenyl magnesium chloride, or you could do phenyl magnesium bromide, or phenyl magnesium iodide. Just anything that gives you kind of phenyl minus. And phenolithium does that. The Grignards, whether it's the chloride, bromide, or iodide, all those give you this reactive species, which is really what's doing the reaction. And of course, we will need, I won't draw the tetrahedral intermediate, but we're going to form one in this after the end of this first step. And so we need a second step of water or something to protonate our tetrahedral intermediate and get this alcohol product. All right, problem number 6. Again, now this looks a little different, but the left-hand side of the slide looks about the same. We start with a carbonyl. In this case, it's an aldehyde, and we get an alcohol in the middle. And what's new? Well, this isopropyl group is new. Now, we'll take care of the next step in just a minute, but we need something in this box that's going to account for the addition of that alkyl group. And note that even though I haven't drawn it, that hydrogen is there. So that hydrogen did not go anywhere. It's still there, but what's been added is this isopropyl. So that is going to be our nucleophile. We need an isopropyl, and we'll just make it a Grignard. Note that this isopropyl group has 1, 2, 3 carbons. So we need to make sure our Grignard reagent, as our reagent, also has 3 carbons. And of course, we're going to need a second step to protonate the tetrahedral intermediate. Now, let's deal with this second part of the slide. So we're going from an alcohol, everything's kind of the same except for going from an alcohol to a carbonyl. And notice, there is no additional hydrogen, so we have to lose this hydrogen as well. This is an oxidation. And the point of this problem is to show that, hey, once you do an addition, you're not stuck with that alcohol. You can do other things with that alcohol. It's just an alcohol. And so one thing you do to alcohols pretty often is you will do an oxidation. So we could use an oxidant like PCC. PCC will perform that oxidation and form this carbonyl product. So that's part of the beauty of these reactions. We form alcohols. And alcohols are so flexible. You could reform this carbonyl, and you could attack this carbonyl again to add yet another nucleophile to that carbon. So really flexible chemistry. Don't just always say, okay, I ran the reaction, I got my product. keep in mind that in synthetic chemistry, people look to do additional things with those products. So you may not be done with your synthetic transformations. Okay, what do you know? This problem follows the same sort of pattern as the previous one. On the left, we have a carbonyl, it's an aldehyde, and we do some kind of addition to this carbonyl to get an alcohol. Note that's what's new is this carbon right here. So let's put in our hydrogen. That was formerly the aldehyde proton. It hasn't gone anywhere, but what's new is that methyl. So we know what nucleophile has to be in this box. And there's a subsequent reaction afterwards, and we'll talk about that in just a moment. So we need some kind of methyl nucleophile. Let's just keep it simple. Methyl lithium, we could do methyl Grignard. I mean, there are other forms of methyl minus that we could use, but again, all of these kind of, as long as what's in the box is a source of methyl minus, we're fine. And we'll need a second step to protonate the tetrahedral intermediate with some water. Now, what do we do in this next step? Well, again, we have an alcohol. Now, clearly we haven't oxidized it to a ketone because there's no carbonyl in this product, but we have an alkene. That's okay. We know that alcohols can undergo elimination reactions. And perhaps this has undergone an elimination. One way to do an elimination is just treat this with sulfuric acid and heat. This would be an E1 reaction, and that will give the elimination so that we end up losing a beta hydrogen on the more highly substituted carbon, so that we end up getting the Satsef product as opposed to the Hoffman product. So this is, again, alcohols. They can do a lot of things, not just get oxidized. You can also do eliminations. You know, if you wanted to, you could do something else like treat this with tosyl chloride to make that OH into a leaving group, and then treat with a base like sodium methoxide in methanol. And this would kind of be the E2 pathway to getting to that same alcohol. I'm sorry, not alcohol, the same alkene. Here is our last problem. Note that this sort of breaks the pattern. So we're used to seeing a carbonyl over here. We don't have a carbonyl. However, when we look, we do finish with an alcohol, and we have added some carbons here. So let's number these up. There's 5 carbons. Those 5 carbons are still there. But let's label that A and B just to show those are different. So we have added carbons. And this would be great. We know how to add carbons, but we need a carbonyl over here, not an alcohol. That's okay. We can do that. We know how to convert an alcohol into a carbonyl, and that would involve like some kind of oxidation. I used PCC in a previous reaction. You can do the Swern oxidation. So let's write that product. So let's do the Swern. Now I know this is a 5-carbon chain. I'm just going to draw out a 5-carbon chain. And there's our double bond. And here now is our aldehyde from that Swern oxidation. Now this looks more normal. We have a carbonyl, and we're going to get an alcohol by adding 2 carbons. So let's write out our 2-carbon nucleophile. And that might be, I think we used this reagent earlier, ethyl lithium. Let's write that in our box. There are our 2 carbons, and specifically this would be A and that would be B, and that will do our addition reaction. And this addition reaction, there's our original 5 carbons. It's going to be our O minus lithium, and there's A and B, Alpha and Bravo. Fantastic. And now finally, so that's our tetrahedral intermediate. Can't miss saying that. And now we need, this tetrahedral intermediate is going to float around. So what we need is some water, proton source, boom, boom. And that's going to give us our alcohol product. So let's put this in the box. We need water. So again, sometimes you get a group, you may want to add a strong nucleophile to your molecule, a few carbons, but you don't have a functional group that you can work with. You're stuck with this alcohol. That's okay. Oxidize that alcohol. That'll give you the carbonyl, and then you can go ahead and do your attack and get your carbons into your molecule. So a lot of flexibility in this chemistry. Fantastically important synthetic reaction. I hope you enjoyed these problems and that they help you better understand the addition of strong nucleophiles on aldehydes and ketones. Please subscribe to the channel, like this video, or leave a comment. Thank you for watching. Remember that links to these problem sets are in the video description. Take care.